Subscribe so you don't miss out on any of these videos. Exoplanets, or extrasolar planets, are planets that exist outside our solar system, orbiting stars other than our Sun. The exploration of exoplanets has been one of the most exciting and mysterious fields in modern astronomy, with scientists continuously discovering new planets in distant star systems. These planets open up countless possibilities regarding the nature of our universe, the diversity of planetary systems, and the potential for life elsewhere in the cosmos. When it comes to exoplanets, mysteries abound, as we are only beginning to scratch the surface of understanding these distant worlds. The history of exoplanet discovery begins relatively recently. For most of human history, we believe that our solar system might be unique, and the idea of planets around other stars was speculative at best. However, the first confirmed discovery of an exoplanet occurred in 1992 when astronomers Alexander Wolszczyn and Dale Frail identified two planets orbiting a pulsar, a highly magnetized, rotating neutron star. This discovery was surprising because pulsars are remnants of supernova explosions, not the type of stars we would expect to host planets. These planets, called PSR B1257+12b and PSR B1257+12c, were the first indication that planets could exist in extremely hostile and unusual environments. This raised questions about the formation and survival of planets in such regions, opening a door to new ways of thinking about planetary systems. Following this breakthrough, more exoplanets were discovered, but the real game-changer came in 1995 with the discovery of 51 Pegasi b. This was the first exoplanet found orbiting a Sun-like star, and it stunned the scientific community. 51 Pegasi b is a gas giant about half the size of Jupiter, but it orbits its host star at an incredibly close distance, completing an orbit in just 4 days. This was the first hot Jupiter discovery, a category of exoplanets that challenges our understanding of planetary formation. Hot Jupiters are gas giants like our Jupiter, but they orbit extremely close to their stars, resulting in scorching surface temperatures. This was puzzling because gas giants are thought to form in the colder, outer regions of a solar system, yet here was a massive planet extremely close to its star. This discovery led to a broader realization: planetary systems could look vastly different from our own. The neat, orderly arrangement of planets in the solar system, with small rocky planets close to the Sun and gas giants farther away, was not the norm. Instead, the universe appeared to be filled with planets of all types, and all sorts of strange orbits, challenging many of our assumptions about planet formation and stability. Subscribe so you don't miss out on any of these videos. As exoplanet detection methods improved, primarily through techniques like the transit method and radial velocity method, the number of discovered exoplanets grew rapidly. The transit method involves observing a star's brightness as a planet passes in front of it, temporarily dimming the light. This dimming provides crucial information about the size and orbit of the planet. The radial velocity method, on the other hand, detects the gravitational wobble of a star caused by the presence of an orbiting planet. These methods, along with others, have given us a wealth of data about exoplanets, though each discovery often raises as many questions as it answers. One of the most tantalizing aspects of exoplanet research is the search for habitable planets, those that might support liquid water and, by extension, life. This search is often centered around the concept of the habitable zone, or the region around a star where conditions might be just right for water to exist on a planet's surface. While the search for habitable exoplanets is ongoing, one of the most famous candidates is Kepler 452b, discovered by NASA's Kepler Space Telescope. This planet orbits a star very similar to our Sun and is located in the habitable zone. Kepler 452b is about 60% larger than Earth, and while we don't yet know if it has an atmosphere or surface water, its discovery raised hopes of finding Earth-like planets elsewhere in the galaxy. Another exoplanet of great interest is Proxima Centauri b, which orbits the star closest to our solar system, Proxima Centauri. This planet is located within the star's habitable zone and is only about 4.24 light-years away, making it a tantalizing target for future exploration. The proximity of Proxima Centauri b allows scientists to study it in more detail compared to more distant planets, offering a potential window into the characteristics of habitable exoplanets. However, habitability isn't limited to the presence of water or an Earth-like environment. Some scientists speculate that life might exist under conditions we can hardly imagine. For example, super-Earths are exoplanets with masses higher than Earth's but lower than gas giants like Neptune or Uranus. Some of these super-Earths may have thick atmospheres and subsurface oceans, which could provide environments for life to develop in entirely new ways. The discovery of such planets has expanded our understanding of where life might arise, challenging the traditional notions of habitability. One of the great mysteries surrounding exoplanets is their extreme diversity. Planets can be categorized based on their size, mass, and distance from their star, but even within these categories, there is enormous variation. For instance, some gas giants like Jupiter have stable orbits far from their host stars, while hot Jupiters like 51 Pegasi b orbit dangerously close. Similarly, rocky planets can vary in size and composition, with some being true super-Earths, many times the size of our own planet, while others are smaller than Earth but feature extreme geological activity or unusual atmospheric conditions. Understanding why some planetary systems look so different from our own remains one of the biggest challenges in exoplanet science. Another mystery is the prevalence of rogue planets, planets that do not orbit any star but instead wander through space on their own. These planets are difficult to detect, as they do not emit light or heat from a nearby star, but scientists estimate there could be billions of them in our galaxy alone. How these rogue planets form, and how they manage to survive the cold, dark conditions of interstellar space, is an enigma. In addition to rogue planets, the question of super-Earths raises new questions about planet formation. While super-Earths are common in other solar systems, we don't have any in our own. Scientists are unsure why this is the case, as super-Earths seem to form easily in other systems. Their absence in our solar system suggests that there may be something unique about how our planetary system formed or that our models of planet formation are incomplete. The composition and atmosphere of exoplanets are also shrouded in mystery. While telescopes like the Hubble Space Telescope and upcoming missions like the James Webb Space Telescope allow scientists to study exoplanet atmospheres, our understanding is still in its infancy. The atmospheres of exoplanets can vary wildly, from thick, toxic clouds of gas to thin, barely detectable layers. Understanding the atmospheric composition of these distant worlds could provide crucial insights into their potential for habitability and the processes that shape planetary systems. One of the most exciting possibilities is the detection of biosignatures, chemical markers that might indicate the presence of life. Certain gases, such as oxygen and methane, are produced by biological processes, so finding them in an exoplanet's atmosphere could suggest that life exists there. However, the interpretation of such data is complicated. There are non-biological processes that can produce these gases, meaning that detecting a biosignature is not definitive proof of life. Additionally, we must be cautious about applying Earth-based criteria to alien planets. Life on other worlds may have evolved in ways we cannot yet imagine, producing entirely different biosignatures. In recent years, the discovery of exoplanets in multi-star systems has added another layer of complexity to our understanding of these worlds. Most stars in the universe exist in binary or multiple star systems, where two or more stars orbit each other. Planets in these systems must navigate complex gravitational forces, and it's unclear how such forces affect planet formation and stability. Nonetheless, exoplanets have been discovered in binary systems, leading to questions about how planets form and persist in such dynamic environments. Another enigma in the study of exoplanets is the role of magnetic fields. Earth's magnetic field plays a crucial role in protecting life by shielding us from harmful solar radiation. It's possible that exoplanets with strong magnetic fields might have better chances of sustaining life. However, detecting magnetic fields on exoplanets is incredibly difficult with current technology. Scientists are still exploring how magnetic fields form on these distant worlds, and what role they might play in determining habitability. The sheer number of exoplanets continues to astonish scientists. Based on data from missions like Kepler, There are an estimated 100 billion exoplanets in the Milky Way alone. This vast number raises a philosophical question: what are the chances that some of these planets host life? Given the diversity and abundance of planets in our galaxy, many scientists believe that life elsewhere in the universe is not just possible but likely. However, without concrete evidence, this remains one of the greatest unanswered questions in science. As we continue to discover new exoplanets, the possibilities seem endless. With the upcoming launch of advanced telescopes like the James Webb Space Telescope, scientists hope to learn more about the atmospheres, compositions, and potential habitability of these distant worlds. Each discovery brings us one step closer to answering fundamental questions about our place in the universe. Are we alone? What makes a planet habitable? And how diverse can planetary systems truly be? The study of exoplanets, filled with mysteries and unknowns, promises to transform our understanding of the universe for decades to come. One of the biggest mysteries in the study of exoplanets revolves around the formation of planetary systems. The traditional model of planet formation, known as the nebular hypothesis, suggests that planets form from the protoplanetary disk of gas and dust that surrounds a young star. Over time, particles within this disk collide and stick together, gradually building up into larger bodies known as planetesimals. These planetesimals, in turn, collide and merge to form planets. However, the discovery of exoplanets, particularly those that don't fit into our expectations based on the solar system, has revealed that planetary formation is far more complex than this simple model suggests. Hot Jupiters, for example, challenge our understanding of where gas giants form. In our solar system, gas giants like Jupiter and Saturn are located far from the Sun, in the cold outer regions where gas can condense. Yet, hot Jupiters orbit extremely close to their stars, raising questions about how they ended up in such positions. One hypothesis is that these planets formed farther out in their solar systems, and then migrated inward due to interactions with the protoplanetary disk, or other planets. This idea of planetary migration has become a crucial part of modern theories of planetary formation, but the exact mechanisms are still poorly understood. Another complication in the study of planetary formation is the discovery of exoplanets in systems with more than one star. In binary or multiple star systems, the gravitational forces are far more complex than in a single star system like our own. It was initially thought that these chaotic forces would prevent planets from forming or maintaining stable orbits, yet exoplanets have been found in such systems. How planets form and survive in these dynamic environments is still a mystery, and each new discovery challenges our understanding of the processes that govern planetary systems. Additionally, the diversity of exoplanets discovered so far suggests that planet formation is not a uniform process. We've found planets that are nothing like those in our solar system, including super-Earths, mini-Neptunes, and even planets with extreme orbits. Super-Earths are planets with masses between that of Earth and Neptune, and while they are common in other star systems, they are absent in our own solar system. This raises questions about why our system lacks these planets, and whether the processes that shaped our solar system were unique, or simply part of a broader range of planetary formation possibilities. Mini-Neptunes, on the other hand, are smaller than the gas giants we are familiar with but have thick atmospheres of hydrogen and helium. These planets challenge the idea that planets can be easily categorized into rocky or gas giants. The discovery of these intermediate types of planets has forced astronomers to reconsider the boundaries between different classes of planets, and to explore how a planet's size, composition, and distance from its star influence its development. One of the most puzzling aspects of exoplanet research is the variety of planetary orbits. While the planets in our solar system follow nearly circular orbits, many exoplanets have highly elliptical orbits that bring them much closer to and farther from their stars during their journeys around their sun. This raises questions about the stability of such systems, and how these extreme orbits affect the planet's environments. Some scientists believe that interactions between planets, or between planets and their protoplanetary disks, could be responsible for these irregular orbits, but the exact mechanisms remain unclear. Furthermore, the discovery of rogue planets, those that do not orbit any star, has added another layer of complexity to our understanding of planetary formation and stability. Rogue planets are thought to have been ejected from their original star systems, possibly due to gravitational interactions with other planets or stars. These planets drift through interstellar space, cold and isolated, far from the warmth of any star. The existence of rogue planets challenges the traditional view that planets are intrinsically linked to stars and suggests that planetary systems may be more dynamic and chaotic than previously thought. The study of exoplanet atmospheres is another area filled with intrigue and mystery. With current technology, scientists can analyze the atmospheres of some exoplanets, particularly those that pass in front of their stars from our point of view. As the planet transits its star, some of the star's light passes through the planet's atmosphere, allowing astronomers to determine the composition of the atmosphere based on the absorption of different wavelengths of light. This technique has revealed that many exoplanet atmospheres contain exotic compounds, including clouds of molten iron and glass. The presence of these extreme conditions has raised questions about the climate and weather on exoplanets. On hot Jupiters, for example, temperatures can exceed 1000 degrees Celsius, causing metals like iron to vaporize and form clouds. Winds on these planets can reach thousands of kilometers per hour, creating storms that are far more violent than anything we experience on Earth. Understanding how these atmospheres behave and evolve is still a major challenge, as our knowledge of atmospheric dynamics is largely based on Earth and the planets in our solar system. The possibility of detecting signs of life on exoplanets has captivated scientists and the public alike. One way to search for life is to look for biosignatures, gases or other compounds in a planet's atmosphere that are associated with biological activity. For example, on Earth, life produces large amounts of oxygen and methane, so detecting these gases on an exoplanet could be an indication of life. However, interpreting biosignatures is complex. There are non-biological processes that can produce these same gases, so scientists must be cautious in drawing conclusions from such data. Moreover, life on other planets may be very different from life on Earth, producing entirely different biosignatures. One of the key missions in the search for habitable exoplanets is NASA's James Webb Space Telescope, JWST. Scheduled for launch in the coming years, the JWST will be able to study the atmospheres of exoplanets in unprecedented detail. One of its goals is to detect potential biosignatures in the atmospheres of Earth-like planets in the habitable zones of their stars. The JWST represents a major leap forward in our ability to study exoplanets, and could bring us closer to answering the question of whether life exists elsewhere in the universe. While the search for life is a central focus of exoplanet research, scientists are also interested in understanding the fundamental processes that govern planetary systems. For example, the study of planetary composition is crucial for understanding how planets form and evolve. The composition of an exoplanet's atmosphere, surface, and interior can provide clues about its history, including whether it has undergone significant geological or atmospheric changes over time. This is particularly important for understanding planets in the habitable zone, where conditions could potentially support life. One of the mysteries surrounding exoplanets is the role of water in planetary development. On Earth, water is essential for life, and scientists believe that liquid water is one of the key ingredients for habitability. However, detecting water on exoplanets is challenging. While we can detect water vapor in the atmospheres of some gas giants, finding water on smaller, rocky planets is much more difficult. Scientists are also exploring the possibility that water may exist in subsurface oceans on icy moons or planets, which could provide environments for life even if the surface is frozen or inhospitable. In addition to water, scientists are interested in the role of other compounds, such as carbon dioxide and methane, in the atmospheres of exoplanets. These gases play a crucial role in regulating a planet's climate through the greenhouse effect, and their presence or absence can determine whether a planet is too hot, too cold, or just right for liquid water to exist. Understanding the balance of these gases on exoplanets is critical for determining their potential habitability. As we continue to discover new exoplanets, the question of how common Earth-like planets are in the galaxy becomes increasingly relevant. The Kepler Space Telescope, which has discovered thousands of exoplanets, has provided data that suggests Earth-sized planets in the habitable zones of their stars may be relatively common. However, finding a true Earth twin, a planet that closely resembles Earth in size, composition, and distance from its star, has proven to be difficult. Most of the planets discovered so far are either much larger than Earth or are located in extreme environments that make them unlikely candidates for life. Despite these challenges, the discovery of exoplanets like Kepler 452b and Proxima Centauri b has raised hopes that we may eventually find a planet that closely resembles Earth. Kepler 452b, for example, orbits a star very similar to our Sun and is located in the habitable zone, where liquid water could exist. While we don't yet know if this planet has an atmosphere or surface water, its discovery is a tantalizing hint that Earth-like planets may be out there, waiting to be found. The search for Earth-like exoplanets is not just about finding worlds where life might exist, but also about understanding the conditions that make a planet habitable. One of the biggest questions is whether habitability requires a planet to be in the so-called habitable zone, the region around a star where liquid water can exist. Traditionally, this zone is defined by the distance from a star where temperatures are either too hot nor too cold for water to remain in liquid form. However, the discovery of planets with subsurface oceans, such as Jupiter's moon Europa and Saturn's moon Enceladus, suggests that life might not be restricted to planets within the habitable zone. These moons have thick ice shells covering oceans of liquid water, kept warm by tidal heating from their parent planets. The possibility that life could exist in such extreme environments challenges our understanding of habitability and expands the range of places where we might search for life. If life can exist in subsurface oceans, it raises the question of whether similar environments could exist on exoplanets outside the traditional habitable zone. For example, planets orbiting red dwarf stars, which are cooler and smaller than the Sun, may have thick atmospheres that trap heat, allowing liquid water to exist even on planets that are farther from their star. These planets might have surface conditions that are too cold for life as we know it, but subsurface oceans, heated by the planet's interior, could still provide a habitat for life. The discovery of exoplanets around red dwarf stars has been one of the most exciting developments in recent years. Red dwarfs are the most common type of star in the galaxy, making up about 70% of all stars. This means that if planets can be habitable around red dwarfs, the number of potentially life-bearing worlds in the galaxy could be much higher than previously thought. However, red dwarfs present some unique challenges for habitability. Because they are smaller and cooler than the Sun, planets in the habitable zone of a red dwarf must orbit much closer to their star. This can expose the planet to intense stellar activity, including flares and radiation that could strip away the atmosphere or make the surface uninhabitable. One of the best-known examples of an exoplanet orbiting a red dwarf star is Proxima Centauri b, located in the habitable zone of Proxima Centauri, the closest star to our solar system. Proxima Centauri b is slightly larger than Earth and receives about the same amount of energy from its star as Earth does from the Sun, making it a prime candidate for habitability. However, Proxima Centauri is a highly active star, and its frequent flares could pose a threat to any atmosphere the planet might have. Understanding how planets like Proxima Centauri b can survive and maintain habitable conditions in the face of such extreme stellar activity is one of the key challenges for future research. Another mystery surrounding exoplanets is the question of their magnetic fields. On Earth, the magnetic field plays a crucial role in protecting the planet from solar wind and cosmic radiation, which would otherwise strip away the atmosphere and expose the surface to harmful radiation. A planet's magnetic field is generated by the movement of molten metal in its core, and it acts as a shield, deflecting charged particles from the solar wind. Without a magnetic field, a planet's atmosphere could be eroded over time, as is thought to have happened to Mars, which once had a thicker atmosphere and possibly liquid water on its surface. For exoplanets, the presence or absence of a magnetic field could be a critical factor in determining habitability. However, detecting magnetic fields on exoplanets is extremely difficult with current technology. Scientists are exploring indirect methods of detection, such as observing the interaction between the planet and its star's magnetic field. Planets with strong magnetic fields might produce auroras, similar to the northern and southern lights on Earth, which could be detectable from great distances. Understanding the role of magnetic fields in protecting exoplanets is an important area of research, as it could help determine which planets are most likely to support life. The discovery of exoplanets has also raised questions about the diversity of planetary systems in the galaxy. Our solar system has a relatively orderly structure, with small, rocky planets close to the Sun and large, gas giants farther out. However, many exoplanetary systems look very different. Some have gas giants orbiting extremely close to their star, while others have super-Earths or mini-Neptunes in orbits that are much more compact than anything we see in our solar system. This diversity suggests that planetary systems can form in a wide variety of ways, and the processes that shaped our solar system may not be universal. One possible explanation for the diversity of planetary systems is the influence of gravitational interactions between planets. In our solar system, the orbits of the planets are relatively stable, but in other systems, planets may interact more dynamically, leading to migrations, collisions, or even ejections of planets from the system. These gravitational interactions can have a profound impact on the architecture of a planetary system, determining the types of planets that form and where they end up. Understanding these processes is crucial for making sense of the wide range of exoplanetary systems we've observed and for predicting what kinds of planets might be found around different types of stars. The role of the protoplanetary disk, the disk of gas and dust that surrounds a young star and eventually forms planets, is another area of active research. The composition and structure of the protoplanetary disk can influence the types of planets that form and their distribution within the system. For example, the amount of gas in the disk can determine whether gas giants like Jupiter form, while the distribution of solid material can influence the formation of rocky planets like Earth. Variations in the protoplanetary disk from one system to another could explain why some systems have hot Jupiters, while others have only small, rocky planets. The study of exoplanets has also led to new questions about the role of moons in planetary systems. In our solar system, moons play a significant role in shaping the evolution of planets. For example, Earth's moon stabilizes the planet's axial tilt, which helps regulate the climate over long periods of time. Moons can also affect the geological activity of their parent planets, as seen on Jupiter's moon Io, which is the most volcanically active body in the solar system due to tidal forces from Jupiter's gravity. The discovery of exoplanets raises the possibility that moons, or exomoons, could play similar roles in other planetary systems. Detecting exomoons is even more challenging than detecting exoplanets, but there is indirect evidence that some exoplanets might have moons. For example, variations in the timing of a planet's transit across its star could be caused by the gravitational influence of a moon. Scientists are also exploring the possibility that large moons could have atmospheres of their own, creating additional opportunities for life to exist in these systems. The study of exomoons is still in its infancy, but it represents an exciting frontier in the search for habitable environments beyond Earth. One of the ultimate goals of exoplanet research is to determine whether Earth-like planets are common or rare in the universe. This question is central to the search for life beyond our solar system, as it addresses whether the conditions that led to life on Earth are unique, or if they are common throughout the galaxy. The discovery of thousands of exoplanets has provided a wealth of data to begin answering this question, but there is still much we don't know. One approach to answering this question is to study the habitability of exoplanets, whether they have the right conditions for life as we know it. This involves not just the presence of liquid water, but also the right atmospheric conditions, geological activity, and stable climates. Scientists are working to develop models that can predict the likelihood of habitability based on a planet's size, distance from its star, and other factors. As we gather more data from missions like the James Webb Space Telescope, we will gain a better understanding of how common potentially habitable planets are in the galaxy. However, even if Earth-like planets are common, the question of whether life actually exists on these planets remains open. The discovery of life on another planet would be one of the most profound scientific breakthroughs in history, fundamentally altering our understanding of the universe and our place in it. The search for biosignatures, gases or other compounds in a planet's atmosphere that indicate the presence of life, is a major focus of current and future missions. While we have yet to find definitive evidence of life on an exoplanet, the discovery of potentially habitable worlds has brought us closer to answering this age-old question. As we continue to explore the mysteries of exoplanets, new discoveries are reshaping our understanding of the universe. The sheer diversity of planets, from hot Jupiters to icy super-Earths, has shown us that our solar system is just one of many possible outcomes of planetary formation. Each new discovery challenges our assumptions and opens up new possibilities for what planetary systems can look like and where life might exist. The discovery of potentially habitable exoplanets has sparked intense interest in what conditions are necessary for life to emerge and thrive. While liquid water remains the primary criterion for habitability, other factors, such as atmospheric composition, planetary temperature, and geological activity, are equally important. One of the key areas of study is the concept of atmospheric retention, or how well a planet can hold onto its atmosphere over long periods of time. Earth's atmosphere is crucial for maintaining stable temperatures, protecting life from harmful radiation, and providing the gases necessary for respiration. Without a thick, stable atmosphere, even a planet in the habitable zone could be too hostile for life. Several factors influence a planet's ability to retain its atmosphere. The planet's size and gravity play a crucial role, as smaller planets with weaker gravitational pulls may have difficulty holding on to lighter gases like hydrogen and helium. Additionally, the proximity of the planet to its star can affect atmospheric retention. Planets orbiting too close to their star may experience intense radiation and solar winds that strip away their atmospheres over time. This phenomenon has been observed in some exoplanets, where high-energy radiation from their parent stars has been detected eroding their atmospheres. One of the most fascinating aspects of exoplanetary science is the potential for atmospheres vastly different from our own. For example, some exoplanets might have atmospheres rich in hydrogen or methane, creating environments that are inhospitable to life as we know it but could potentially support exotic forms of life. The study of such atmospheres can give us insights into how planets evolve and what conditions might allow for life in forms we can only imagine. Planets with thick, smog-like atmospheres might have surface conditions that are completely alien to anything on Earth, yet still capable of supporting some form of life. One of the most promising methods for studying exoplanet atmospheres is through the technique of transmission spectroscopy. This involves analyzing the light from a star as it passes through a planet's atmosphere during a transit. By examining how the starlight is absorbed at different wavelengths, scientists can infer the composition of the atmosphere, identifying gases like oxygen, carbon dioxide, water vapor, and methane. This technique has already been used to study the atmospheres of several exoplanets, and with upcoming missions like the James Webb Space Telescope, we expect to learn much more about the diversity of planetary atmospheres in the coming years. Atmospheric studies are also crucial for understanding the potential for exoplanets to experience climate stability over long periods. On Earth, the carbon silicate cycle plays a key role in regulating the planet's temperature by controlling the levels of carbon dioxide in the atmosphere. This geological process helps maintain a relatively stable climate over geological timescales, preventing runaway greenhouse effects or global freezing. Whether similar processes operate on exoplanets is an open question, but understanding these mechanisms is vital for assessing long-term habitability. In some cases, a planet's atmosphere could be in a delicate balance with its surface conditions. For example, on Venus, a runaway greenhouse effect led to surface temperatures hot enough to melt lead, despite the planet once being in a potentially habitable zone. The possibility of similar scenarios occurring on exoplanets is one of the key considerations for scientists trying to assess habitability. The detection of excess carbon dioxide or other greenhouse gases in an exoplanet's atmosphere could indicate that the planet is too hot for life, even if it lies within the habitable zone. The discovery of super-Earths, planets that are larger than Earth but smaller than gas giants like Neptune, has added another layer of complexity to the study of exoplanet atmospheres. Super-Earths are particularly intriguing because their larger mass allows them to hold on to thicker atmospheres, which could have a significant impact on surface conditions. Some super-Earths may have dense, water-rich atmospheres, potentially creating conditions that are even more conducive to life than those on Earth. Others might have thick, toxic atmospheres that trap heat, making the surface uninhabitable. Understanding the relationship between a planet's mass, atmosphere, and surface conditions is a critical area of ongoing research. Another mystery surrounding exoplanet atmospheres is the role of clouds. Clouds play a major role in regulating the climate on Earth, reflecting sunlight and helping to cool the planet. On exoplanets, clouds could have a similar effect, but their composition and behavior could be radically different. For example, on some hot Jupiters, clouds made of silicates and metal oxides could exist in the upper atmosphere, reflecting light and creating an opaque appearance. On cooler planets, clouds of water vapor, methane, or ammonia might dominate. Understanding how clouds form and evolve on exoplanets is essential for predicting their climates and, by extension, their habitability. While much of the focus in exoplanet research has been on finding planets that are similar to Earth, there is also great interest in studying planets that are radically different. Gas giants like Jupiter and Saturn, for example, are not habitable in the traditional sense, but they offer valuable insights into planetary formation and the dynamics of planetary systems. Gas giants can act as gravitational anchors, shaping the orbits of other planets in the system and potentially protecting inner rocky planets from comet impacts, as Jupiter does in our solar system. Studying gas giants around other stars helps us understand the full range of planetary systems and the role that these massive planets play in shaping their environments. Hot Jupiters, in particular, have been a source of fascination since their discovery. These are gas giants that orbit extremely close to their parent stars, completing an orbit in just a few days. The existence of hot Jupiters was unexpected, as no planets like them exist in our solar system. Their discovery challenged existing models of planetary formation, which suggested that gas giants could only form far from their stars, where it's cold enough for gas to condense. The presence of hot Jupiters suggests that these planets may have formed farther out in their systems, and then migrated inward due to interactions with the protoplanetary disk or other planets. The migration of hot Jupiters raises important questions about the stability of planetary systems. If a giant planet can move from the outer regions of a system to a close orbit around its star, it could disrupt the orbits of other planets, potentially ejecting them from the system or sending them into unstable orbits. Understanding how planetary migration occurs and what impact it has on the rest of the system is crucial for making sense of the diversity of exoplanetary systems we observe. It also has implications for the search for habitable planets, as the migration of giant planets could make it more difficult for rocky planets to maintain stable, life-friendly orbits. One of the most intriguing aspects of exoplanetary science is the search for so-called water worlds, planets that are covered in vast oceans. These planets could have conditions that are very different from Earth's, with no land masses and deep, global oceans that might harbor life. Water worlds are thought to be common among super-Earths, as their larger mass allows them to hold onto thick atmospheres and vast amounts of water. However, life on such planets would face unique challenges, particularly if there is no land to support the development of complex ecosystems. The deep oceans could also isolate any potential life from the energy sources needed to drive evolution, such as sunlight or geothermal activity. The study of exoplanets has also raised important questions about the potential for life to exist in environments that are vastly different from those on Earth. While Earth-like planets in the habitable zone are the most obvious candidates for life, the discovery of extremophiles, organisms that thrive in extreme environments on Earth, suggests that life could exist in a wide range of conditions. For example, some extremophiles live in the deep ocean near hydrothermal vents, where there is no sunlight and temperatures are near boiling. Others thrive in acidic lakes, radioactive environments, or deep underground. The existence of extremophiles opens up the possibility that life could exist on planets that are much more hostile than Earth. One of the most exciting prospects in exoplanetary science is the potential for finding biosignatures, indicators of life, in the atmospheres of distant planets. Biosignatures could take the form of gases like oxygen, methane, or nitrous oxide, which are produced by biological processes. The detection of these gases in an exoplanet's atmosphere would not necessarily prove the existence of life, as they could also be produced by non-biological processes, but it would be a strong indication that life could be present. The search for biosignatures is one of the primary goals of upcoming space missions, and the discovery of even a single biosignature would be a groundbreaking achievement. As we continue to discover more exoplanets, the question of whether we are alone in the universe becomes more pressing. The discovery of thousands of exoplanets has shown that planets are common throughout the galaxy, and many of them have the potential to be habitable. However, finding life is another challenge entirely. Even if a planet has the right conditions for life, we may never know for certain without direct evidence. The search for life on exoplanets is one of the greatest scientific endeavors of our time, and while the discovery of life beyond Earth remains elusive, each new discovery brings us closer to answering one of the most profound questions in science. The potential for life on exoplanets is not just a scientific curiosity, but also a philosophical and existential one. If we were to find evidence of life on another planet, it would fundamentally change our understanding of our place in the universe. For centuries, humans have wondered whether we are unique, or whether life exists elsewhere, and the discovery of life on exoplanets would suggest that life is likely a common outcome in the universe. This would raise profound questions about the nature of life, its origins, and the factors that contribute to its emergence. Are there universal principles that guide the development of life, or is it the result of a complex and perhaps even random set of conditions? Another fascinating question raised by the study of exoplanets is whether there could be intelligent life elsewhere in the universe. While most of the focus has been on finding microbial life, the possibility of intelligent extraterrestrial civilizations remains an open question. The discovery of a planet with Earth-like conditions does not necessarily mean that intelligent life will develop there, as many other factors come into play, such as evolutionary pressures and the stability of the environment over time. However, the sheer number of exoplanets suggests that, given the right conditions, intelligent life could arise on multiple planets across the galaxy. One of the major challenges in the search for intelligent extraterrestrial life is the vast distances between stars. Even if an intelligent civilization exists on a distant exoplanet, the odds of detecting them are slim due to the limitations of current technology. Radio waves, the primary method used by programs like SETI, search for extraterrestrial intelligence, to search for alien civilizations, weaken as they travel across space, and a signal from a distant planet might be too faint for us to detect. Moreover, intelligent civilizations might not use radio waves at all, or they could be using communication technologies that we haven't yet developed or even conceived of. The potential for communication with extraterrestrial civilizations raises another set of questions. How would we communicate with them, and what would we say? Any communication with an alien civilization would likely be limited to simple messages, as the vast differences in language, culture, and biology would make meaningful communication extremely difficult. There are also ethical considerations involved in contacting extraterrestrial civilizations, particularly if they are less technologically advanced than we are. Would it be right to interfere with their natural development, or could contact with Earth pose a threat to their society? Another area of active research in exoplanetary science is the study of planetary systems and how they compare to our own solar system. One of the most surprising findings in exoplanet research is the diversity of planetary systems. While our solar system has a relatively neat arrangement of rocky planets close to the Sun and gas giants farther out, many exoplanetary systems do not follow this pattern. Some systems have hot Jupiters orbiting extremely close to their stars, while others have planets in highly elliptical orbits or planets that are significantly larger or smaller than anything in our solar system. This diversity suggests that the processes that govern planetary formation and evolution are far more complex than we originally thought. The arrangement of planets in a system can have a major impact on the potential for life. For example, giant planets like Jupiter can act as protectors, shielding inner rocky planets from comet and asteroid impacts. However, in some systems, the presence of a hot Jupiter could disrupt the orbits of other planets, making it difficult for stable, life-friendly environments to exist. The study of exoplanetary systems helps us understand the range of possibilities for planetary formation and the conditions that might allow for life to develop and persist. One of the most exciting developments in exoplanet research is the potential for direct imaging of exoplanets. Currently, most exoplanets are detected indirectly through methods like the transit method or radial velocity method, which rely on the effects that planets have on their parent stars. However, advancements in telescope technology are bringing us closer to the ability to directly observe exoplanets. Direct imaging would allow scientists to study the planets themselves, rather than just their effects on their stars, and could provide critical insights into their atmospheres, surface conditions, and potential for life. Direct imaging of exoplanets is incredibly challenging due to the brightness of their parent stars, which can overwhelm the faint light reflected by the planets. However, techniques like coronagraphy, which blocks out the light from the star, and the use of space-based telescopes located far from Earth's atmosphere, are improving our ability to directly observe exoplanets. The upcoming James Webb Space Telescope, along with other next-generation observatories, will likely play a key role in this effort, and the direct observation of an Earth-like exoplanet could be one of the major scientific milestones of the coming decades. The possibility of finding Earth-like planets in other star systems has also driven interest in the concept of the habitable zone, the region around a star where conditions are right for liquid water to exist. However, the definition of the habitable zone is evolving as scientists gain a better understanding of planetary systems. While the presence of liquid water is still considered a key criterion for habitability, other factors, such as the planet's atmosphere, geological activity, and magnetic field, are also important. For example, a planet outside the traditional habitable zone might still support life if it has a thick atmosphere that traps heat, or if it experiences tidal heating due to interactions with other planets or moons. Some scientists have proposed the existence of superhabitable planets, worlds that are even more conducive to life than Earth. These planets might be slightly larger than Earth, with thicker atmospheres and more stable climates. They could also have more diverse ecosystems, with a wider range of environments where life could thrive. The discovery of such planets would have profound implications for our understanding of habitability, and could suggest that Earth is not the optimal environment for life, but rather just one of many possible configurations that could support living organisms. Another intriguing area of research is the study of exomoons, moons orbiting exoplanets. While no exomoons have been definitively confirmed yet, their existence is likely, given the prevalence of moons in our own solar system. Exomoons could potentially be habitable, especially if they orbit gas giants in the habitable zone. The discovery of a habitable exomoon would expand the range of environments where life could exist and provide new opportunities for studying the conditions necessary for life. Exomoons might also experience tidal heating, which could create geothermal energy sources that support life, even if the moon is too far from its star to receive significant sunlight. As the study of exoplanets continues to advance, one of the most exciting prospects is the possibility of sending spacecraft to explore them. While interstellar travel remains a distant dream, initiatives like Breakthrough Starshot are exploring the possibility of sending small, fast-moving spacecraft to nearby star systems. These spacecraft, powered by laser-driven sails, could potentially reach speeds of up to 20% the speed of light, allowing them to reach nearby star systems like Alpha Centauri within a few decades. While these missions would not carry humans, they could provide invaluable data on the planets and stars in these systems, bringing us closer to the goal of exploring exoplanets firsthand. The study of exoplanets is also driving interest in the possibility of terraforming, modifying planets to make them more Earth-like and habitable for humans. While the idea of terraforming has been popularized by science fiction, scientists are beginning to explore the technical and ethical challenges involved in such an endeavor. Terraforming would likely require massive engineering projects, such as altering a planet's atmosphere, temperature, and surface conditions. The ethical considerations are also significant, particularly if there is a possibility of indigenous life on the planet. The question of whether we have the right to alter other planets for our own benefit is a complex one, and the discovery of life on exoplanets could complicate these discussions further. One of the greatest mysteries surrounding exoplanets is the question of how common life is in the universe. The discovery of extremophiles on Earth has expanded our understanding of the conditions in which life can exist, suggesting that life might be more adaptable than we previously thought. However, despite the vast number of exoplanets discovered, we have yet to find definitive evidence of life. This raises the question of whether life is rare and difficult to start, or whether it is common but difficult to detect. The answer to this question could have profound implications for our understanding of biology, evolution, and the nature of life itself. The future of exoplanet research is incredibly promising, with new discoveries being made regularly and advancements in technology bringing us closer to answering some of the biggest questions in science. Upcoming missions like the James Webb Space Telescope, the European Space Agency's Plato mission, and NASA's upcoming LUVOIR Observatory are expected to revolutionize our understanding of exoplanets, providing detailed information on their atmospheres, surface conditions, and potential for habitability. These missions, along with continued advancements in ground-based telescopes and computational models, will help us unravel the mysteries of exoplanets and bring us closer to finding life beyond Earth. As we look to the future, the study of exoplanets holds the potential to transform our understanding of the universe and our place in it. Each new discovery brings us closer to answering some of the most fundamental questions in science. How common are planets like Earth? What conditions are necessary for life to exist? And are we alone in the universe, or is life a common outcome of the cosmic processes that govern the formation of planets and stars? The answers to these questions will not only expand our knowledge of the cosmos but also deepen our understanding of life itself. The sheer variety of exoplanets that have been discovered also highlights the incredible diversity of planetary systems in the universe. Exoplanets come in a wide range of sizes, compositions, and orbits, from massive gas giants to small rocky worlds, and from planets that orbit their stars in mere hours to those with orbits spanning many years. This diversity challenges our understanding of planet formation and forces us to rethink many of the assumptions that were based solely on observations of our own solar system. One of the most surprising discoveries in exoplanet research has been the detection of hot Jupiters, giant gas planets that orbit very close to their parent stars. These planets defy traditional models of planetary formation, which suggests that gas giants should form far from their stars where the temperature is cool enough for gases to condense. The existence of hot Jupiters raises questions about how they formed and migrated to their current orbits. Some theories suggest that they may have formed farther out in their planetary systems and were later pulled inward by gravitational interactions with other planets, or with the protoplanetary disk. The study of hot Jupiters has provided valuable insights into the complex dynamics of planetary systems and the forces that can shape their evolution. Another intriguing class of exoplanets is the super-Earths, which are planets with masses larger than Earth but smaller than gas giants like Neptune. Super-Earths are particularly interesting because they could potentially have conditions suitable for life, depending on their atmospheres and surface compositions. Some super-Earths may have thick atmospheres that create a greenhouse effect, while others may be more Earth-like, with rocky surfaces and liquid water. The study of super-Earths is helping scientists refine their understanding of habitability and the range of planetary environments that could support life. In addition to hot Jupiters and super-Earths, astronomers have also discovered planets in a variety of unusual configurations. Some planets orbit two stars in a binary system, creating a double sunset effect similar to what was famously depicted in the Star Wars universe. These so-called circumbinary planets are a reminder that planetary systems can take many different forms, and they challenge our assumptions about the stability of orbits in multi-star systems. The discovery of circumbinary planets raises questions about how planets form and survive in such complex gravitational environments. Some planets have highly elliptical orbits, meaning that their distance from their star changes dramatically over the course of their year. This can result in extreme temperature variations, with the planet swinging between scorching heat when it is close to the star and freezing cold when it is farther away. These extreme conditions make it unlikely that life as we know it could exist on such planets, but they offer important clues about the forces that shape planetary orbits and the potential for dynamic changes in planetary environments. In recent years, astronomers have also detected rogue planets, planets that do not orbit any star and instead drift through interstellar space. These rogue planets are thought to have been ejected from their original planetary systems due to gravitational interactions with other planets or stars. The existence of rogue planets raises the possibility that there could be many more planets in the universe than we currently know about, as these free-floating worlds would be extremely difficult to detect. Rogue planets also present a unique set of challenges for understanding planetary formation and evolution, as their isolation from stars means they must have very different energy sources and environments. Another area of active research in exoplanetary science is the study of exoplanet atmospheres. The composition of a planet's atmosphere can provide critical clues about its potential for habitability, and the processes that shape its environment. One of the most important breakthroughs in exoplanet research has been the ability to analyze the atmospheres of distant planets through a technique called transmission spectroscopy. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere, allowing scientists to study the absorption patterns and determine the composition of gases in the atmosphere. Transmission spectroscopy has already led to some exciting discoveries, including the detection of water vapor, carbon dioxide, methane, and other gases in the atmospheres of exoplanets. These gases are important indicators of the planet's climate and chemistry, and could potentially be signs of biological activity. For example, methane is a gas that can be produced by biological processes on Earth, so its presence in an exoplanet's atmosphere could be a potential biosignature, though it can also be produced through geological processes. Detecting these gases is a step toward understanding the habitability of exoplanets and the conditions that could support life. Another method used to study exoplanet atmospheres is called direct imaging, where astronomers block out the light from the star to capture the faint light reflected or emitted by the planet itself. This method allows for a more detailed study of the planet's atmosphere and surface conditions, though it is extremely challenging due to the brightness of the parent star. The development of new telescopes, such as the James Webb Space Telescope, is expected to revolutionize direct imaging and provide much more detailed information about the atmospheres of exoplanets. The study of exoplanet atmospheres is also important for understanding the processes that shape planetary climates. Some planets may have runaway greenhouse effects, where thick atmospheres trap heat and cause the planet's surface to become extremely hot, similar to what has happened on Venus. Others may have thick clouds that reflect sunlight, keeping the planet cooler. Understanding these atmospheric processes is key to determining whether a planet could support life or whether it has undergone extreme climate changes that make it inhospitable. One of the most exciting prospects in exoplanetary science is the search for biosignatures, indicators of life in the atmospheres of distant planets. While the detection of water or methane is an important step, scientists are also looking for more complex signatures of life, such as the presence of oxygen or ozone, which on Earth are produced by biological processes. The discovery of such biosignatures on an exoplanet would be a major milestone in the search for life beyond Earth, though confirming that these signals are truly signs of life and not the result of non-biological processes will be a significant challenge. Beyond the search for life, exoplanet research also has the potential to answer fundamental questions about the formation and evolution of planetary systems. By studying the wide variety of exoplanets and their orbits, scientists are gaining new insights into how planets form and migrate within their systems. The discovery of so many planets with unusual characteristics, such as hot Jupiters and highly elliptical orbits, suggests that planetary systems are shaped by complex interactions between planets, stars, and the surrounding protoplanetary disk. These interactions can lead to dramatic changes in planetary orbits and environments, and understanding them is key to unraveling the mysteries of planetary formation. Another important question in exoplanet research is the role of planetary collisions and mergers in shaping planetary systems. The early stages of planet formation are thought to be chaotic, with planets colliding and merging to form larger bodies. These collisions can have a major impact on the final configuration of a planetary system, and they may explain some of the unusual features observed in exoplanetary systems, such as planets with highly inclined orbits, or planets that have lost their atmospheres due to giant impacts. The study of exoplanets is also shedding light on the relationship between planets and their parent stars. A planet's orbit, composition, and atmosphere are all influenced by the characteristics of its star, including its mass, temperature, and activity level. For example, planets orbiting around small, cool stars like red dwarfs may experience tidal locking, where one side of the planet always faces the star, resulting in extreme temperature differences between the day and night sides. Planets orbiting very active stars may also be subject to intense radiation, which can strip away their atmospheres and make them less hospitable to life. As more exoplanets are discovered and studied, scientists are also exploring the possibility that planetary systems like our own are rare or even unique. While many exoplanetary systems have been found, none have been shown to exactly match the structure of our solar system, with its relatively orderly arrangement of planets. This has led to speculation that our solar system may have undergone a different evolutionary path than most, or that the specific conditions that allowed for the development of life on Earth may be rare in the universe. The search for Earth-like exoplanets, planets that are similar in size, composition, and distance from their stars to Earth, remains a major focus of exoplanet research. While several candidates have been identified, including planets in the habitable zones of their stars, none have yet been confirmed to be true Earth analogues. However, as technology continues to improve and more exoplanets are discovered, the chances of finding a true Earth twin increase. Such a discovery would have profound implications for our understanding of habitability and the potential for life beyond our solar system. In addition to the search for Earth-like planets, scientists are also exploring the possibility that life could exist in environments very different from Earth. Some exoplanets may have subsurface oceans, protected from the harsh conditions on the surface by thick ice layers. Others may have atmospheres rich in exotic chemicals that could support forms of life very different from those found on Earth. The discovery of such life would force us to rethink our definitions of habitability and the conditions necessary for life to exist. The study of exoplanets has opened up a new frontier in astronomy, providing a wealth of data and posing new questions about the universe and our place in it. As we continue to explore the vast array of planets beyond our solar system, we are gaining a deeper understanding of the diversity of planetary environments and the complex processes that shape them. Each new discovery brings us one step closer to answering some of the most profound questions in science. How common are planets like Earth? What are the conditions necessary for life to exist? And are we alone in the universe? The potential discovery of life on an exoplanet would be one of the most significant scientific breakthroughs in history. As we explore exoplanets further, we are not just looking for planets that mirror Earth but also expanding our understanding of where life could exist. The search for life is no longer confined to the so-called Goldilocks zone, the region around a star where conditions might be just right for liquid water to exist. Scientists are now considering a wider range of possibilities, including planets or moons with subsurface oceans, or even worlds with atmospheres that support alternative biochemistries. One exciting possibility is that life could exist on a type of planet called an ocean world, where a deep ocean covers the entire surface. These planets might not need to rely on the warmth of their parent stars to maintain liquid water. Instead, they could be heated by geothermal energy from their interiors, similar to the deep-sea hydrothermal vents on Earth that support unique ecosystems. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, are examples of such worlds in our solar system, and similar planets, or moons, may exist in other planetary systems. The discovery of exoplanets with vast oceans opens up intriguing possibilities for life in environments that are very different from our own. Another possibility is the existence of superhabitable planets, worlds that might be even more conducive to life than Earth. Such planets might be slightly larger than Earth, with thicker atmospheres that offer more protection from harmful radiation and better heat retention. They might orbit stars that are more stable and longer-lived than our Sun, giving life more time to evolve and develop. While Earth is often used as the standard for habitability, there is no reason to assume it is the best possible environment for life. The concept of superhabitable planets challenges us to think beyond Earth and consider a wider range of planetary conditions that could support life. In the search for habitable exoplanets, one of the most important factors is the stability of the planet's environment. For life to thrive, a planet's climate needs to remain stable over long periods. Planets with highly eccentric orbits, for example, might experience extreme variations in temperature as they move closer to and farther from their parent stars, making it difficult for life to take hold. Similarly, planets orbiting active stars that emit large amounts of radiation might be subject to frequent and intense solar flares, which could strip away atmospheres and render the surface uninhabitable. The study of exoplanets is helping scientists understand the delicate balance of factors that contribute to planetary habitability. Exoplanet research is also providing new insights into the potential for life on planets that are very different from Earth. For example, some exoplanets may have atmospheres rich in hydrogen or methane, which could create conditions for alternative forms of life. On Earth, most life forms rely on oxygen for respiration, but in other environments, life might use different chemical processes. The study of extremophiles, organisms on Earth that live in extreme environments, such as deep-sea vents or acidic lakes, has shown that life can survive in a wide range of conditions, suggesting that life on other planets might not require the same conditions as life on Earth. The search for exoplanets has also led to a deeper understanding of planetary system formation and evolution. Early theories of planet formation were largely based on our own solar system, with the assumption that other planetary systems would look similar. However, the discovery of exoplanets has shown that planetary systems can be far more diverse and complex than previously thought. Some planetary systems have gas giants orbiting extremely close to their stars, while others have planets in highly elliptical orbits. These discoveries have forced scientists to revise their models of planet formation and migration, leading to new theories about how planets form, move, and evolve over time. One of the key challenges in understanding exoplanets is determining their composition. The mass and size of an exoplanet can provide clues about its makeup, whether it is a gas giant like Jupiter, a rocky planet like Earth, or something in between. However, there is still much we don't know about the internal structures of exoplanets and how their compositions affect their atmospheres, climates, and potential for habitability. New techniques, such as measuring the gravitational effects of exoplanets on their parent stars or analyzing the light from the planet's atmosphere, are helping scientists gather more detailed information about the composition of distant planets. The next frontier in exoplanet research is the direct imaging of exoplanets, which will allow scientists to study them in greater detail. While most exoplanets have been discovered through indirect methods, such as observing the effects of a planet on its star, direct imaging would allow astronomers to capture actual pictures of exoplanets. This is extremely challenging due to the brightness of the parent stars, but new technologies, such as the development of more powerful telescopes and the use of star shading techniques, are bringing us closer to achieving this goal. Direct imaging would provide invaluable data about the atmospheres, surfaces, and potential habitability of exoplanets. One of the most promising developments in the search for habitable exoplanets is the upcoming generation of space telescopes, such as the James Webb Space Telescope, JWST. These new instruments will have the capability to detect and analyze the atmospheres of exoplanets with unprecedented precision. JWST, for example, will be able to study the light passing through the atmospheres of exoplanets, allowing scientists to determine their chemical composition and potentially detect signs of life. The ability to study exoplanet atmospheres in detail is a major step forward in the search for habitable worlds and the quest to answer the age-old question: are we alone in the universe? As exoplanet research continues, one of the most exciting possibilities is the discovery of Earth-like planets in the habitable zones of their stars. The habitable zone is the region around a star where conditions might be just right for liquid water to exist on a planet's surface, a key requirement for life as we know it. While several potentially habitable exoplanets have already been discovered, none have yet been confirmed to be true Earth analogs. The discovery of such a planet would be a major milestone in the search for extraterrestrial life and could provide a new target for future exploration. The study of exoplanets is also helping us understand more about the early history of our own solar system. By observing other planetary systems, scientists can gain insights into the processes that shaped our own system billions of years ago. For example, the discovery of planets with highly elliptical orbits or unusual compositions may provide clues about the collisions and migrations that occurred during the early stages of planet formation. Similarly, the study of exoplanet atmospheres can shed light on the processes that shaped Earth's atmosphere and climate, offering a new perspective on the conditions that made life possible on our planet. In the coming decades, the search for exoplanets is expected to accelerate as new technologies and missions come online. Space missions such as the Transiting Exoplanets Survey Satellite, TESS, and the European Space Agency's Plato mission are designed to find and study exoplanets, particularly those that are similar in size and composition to Earth. These missions will provide valuable data about the frequency and distribution of exoplanets, helping scientists answer fundamental questions about the formation and evolution of planetary systems. The continued discovery of exoplanets is likely to reshape our understanding of the universe and our place within it. The study of exoplanets is not just about finding new worlds, it is also about understanding the fundamental processes that govern the universe. By studying exoplanets, scientists are learning more about how planets form, how they interact with their stars, and how they evolve over time. This research is helping to answer some of the most profound questions in science, including the origins of life and the conditions necessary for life to exist. As we continue to explore the vast array of exoplanets in the universe, we are gaining a deeper appreciation of the diversity and complexity of planetary systems and the possibilities for life beyond Earth. The discovery of exoplanets has opened a new chapter in our understanding of the cosmos, bringing with it both excitement and mystery. One of the most compelling aspects of exoplanet exploration is how it forces us to rethink the uniqueness of our solar system. As astronomers continue to observe a wide variety of exoplanets, they are encountering systems that challenge preconceived notions of what planetary systems should look like. From hot Jupiters orbiting perilously close to their stars to rogue planets that drift through interstellar space untethered to any star, the diversity of these systems has surprised even the most seasoned scientists. For example, the discovery of hot Jupiters was particularly unexpected. These gas giants, similar in size to Jupiter, orbit very close to their parent stars, so close that their atmospheres are heated to thousands of degrees. In our solar system, gas giants like Jupiter and Saturn are located far from the Sun, where the temperature is much lower, and their formation is believed to have required cold environments. The existence of hot Jupiters challenges our understanding of planetary formation and migration. These planets are thought to have formed farther out in their systems and then migrated inward, but the exact mechanisms behind this process are still not fully understood. One hypothesis for how hot Jupiters move inward is that gravitational interactions with other planets, or with the protoplanetary disk in which they formed, caused them to spiral toward their parent stars. Another possibility is that hot Jupiters formed in situ, closer to their stars, but this would require significant revisions to our models of planet formation, as it's currently believed that gas giants need cooler temperatures to accumulate the vast amounts of gas that form their atmospheres. Studying these planets offers key insights into the dynamics of planetary systems and how they evolve over time. Beyond hot Jupiters, astronomers have discovered a whole class of planets known as super-Earths. These are rocky planets larger than Earth but smaller than gas giants like Neptune. Super-Earths are intriguing because they don't exist in our solar system, yet they appear to be very common elsewhere in the universe. They offer a unique opportunity to study planetary compositions and atmospheres that differ from anything we see in our solar system. Some super-Earths may have thick, gaseous atmospheres, while others could be more Earth-like with rocky surfaces and thin atmospheres. The atmospheres of exoplanets are an area of intense study because they can reveal so much about a planet's potential habitability. By analyzing the light that passes through or reflects off a planet's atmosphere, scientists can determine its chemical composition. This technique, known as spectroscopy, allows researchers to identify gases such as water vapor, carbon dioxide, and methane, all of which are key indicators of whether a planet could support life. For example, the presence of water vapor could suggest that liquid water, a crucial ingredient for life as we know it, exists on the planet's surface. In recent years, astronomers have made significant strides in detecting exoplanet atmospheres. The Hubble Space Telescope, for instance, has been used to study the atmospheres of several exoplanets, and the upcoming James Webb Space Telescope promises to take this research to the next level. JWST will be able to analyze the atmospheres of smaller, potentially Earth-like planets with unprecedented precision, allowing scientists to search for biosignatures, chemical indicators of life. A biosignature could be something like an unusually high concentration of oxygen or methane, which on Earth are byproducts of biological processes. The possibility of finding biosignatures on exoplanets raises profound philosophical and scientific questions. What would it mean to discover life beyond Earth? How would it change our understanding of biology, evolution, and the place of humanity in the universe? While many scientists caution that the discovery of a biosignature wouldn't necessarily confirm the presence of life, it would be a major step toward answering one of the most fundamental questions humans have ever asked. Are we alone in the universe? Another fascinating aspect of exoplanet research is the study of planetary climates and weather patterns. While the concept of weather on distant planets might seem like science fiction, astronomers have already observed signs of complex weather systems on some exoplanets. For example, researchers have detected strong winds and extreme temperature variations on hot Jupiters, where the day side of the planet is blasted with heat from the star, while the night side remains much cooler. Some hot Jupiters have temperatures so high that their atmospheres contain vaporized metals, leading to the possibility of exotic weather phenomena such as iron rain. In one particularly intriguing case, astronomers studying the exoplanet HD 189733b observed the presence of silicate particles in the planet's atmosphere, suggesting that this distant world might experience glass rain. While these extreme weather patterns are far removed from anything we experience on Earth, they offer a glimpse into the diverse and sometimes bizarre conditions that exist on planets beyond our solar system. One of the most exciting recent developments in exoplanet science is the discovery of planets orbiting stars other than typical main-sequence stars like our Sun. For example, planets have been found orbiting pulsars, highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation. These planets, known as pulsar planets, are incredibly rare, and their existence raises intriguing questions about how planets could form and survive in such extreme environments. Pulsar planets likely formed from the debris left over after the supernova explosion that created the neutron star, and studying them could provide valuable insights into the processes that govern planet formation in the aftermath of stellar death. In addition to pulsar planets, there is growing interest in finding planets around white dwarfs, the remnants of stars that have exhausted their nuclear fuel and shed their outer layers. Although white dwarfs no longer produce energy through fusion, they can still retain planets in orbit. In fact, recent discoveries have identified planets and planetary debris around white dwarfs, suggesting that some planetary systems may survive the violent end stages of their parent stars' lives. Studying these systems could offer clues about the long-term stability of planetary systems and the potential for life to persist even after a star has died. One of the most mysterious and elusive classes of exoplanets are rogue planets, planets that do not orbit any star but instead drift through interstellar space. These planets were likely ejected from their original planetary systems through gravitational interactions with other planets or stars. Rogue planets are difficult to detect because they don't emit light or reflect the light of a nearby star, but astronomers have developed techniques to identify them by observing how their gravity bends the light of distant stars in a process known as gravitational microlensing. The discovery of rogue planets raises the possibility that there are billions, or even trillions, of these wandering worlds in our galaxy alone. The existence of rogue planets also poses intriguing questions about the potential for life in the absence of a parent star. While it seems unlikely that life could survive on a rogue planet without the warmth and energy provided by a star, it is not entirely out of the question. If a rogue planet had a thick atmosphere or subsurface ocean, it could retain enough heat from its formation or from radioactive decay in its core to support microbial life. This possibility expands the range of environments in which we might search for life beyond Earth, challenging the idea that a star is necessary for a planet to be habitable. As we continue to explore exoplanets, one of the most exciting possibilities is the discovery of Earth-sized planets in the habitable zones of their stars. While many exoplanets have been discovered in these regions, finding planets that are truly Earth-like, rocky planets with similar sizes, compositions, and climates, remains a challenge. The discovery of such a planet would be a major milestone in the search for extraterrestrial life, as it would provide the best opportunity to study a world that might be capable of supporting life as we know it. In the search for habitable exoplanets, scientists are also considering the role of moons. Just as Jupiter's moon Europa and Saturn's moon Enceladus are thought to harbor subsurface oceans that could potentially support life, it's possible that exomoons, moons orbiting exoplanets, could also be habitable. While no exomoons have yet been confirmed, the search is ongoing, and the discovery of a habitable exomoon would be a major breakthrough in our understanding of where life might exist in the universe. The search for exoplanets has also led to the discovery of water worlds, planets that are thought to have deep oceans covering their entire surfaces. These planets could be completely devoid of land, with oceans that are hundreds or even thousands of kilometers deep. Water worlds are of particular interest because liquid water is one of the key ingredients for life as we know it. If these planets have the right conditions, their oceans could potentially support life, either in the form of microbial organisms or more complex creatures. Water worlds present unique challenges for habitability. On Earth, much of the planet's geological activity, such as volcanic eruptions and the movement of tectonic plates, is driven by the interaction between the solid land masses and the planet's atmosphere and oceans. This geological activity plays a crucial role in regulating the Earth's climate and maintaining conditions that are favorable for life. In the case of water worlds, however, the lack of exposed land might limit these processes, making it more difficult for the planet to maintain a stable climate over long periods. Despite these challenges, water worlds remain a tantalizing target in the search for life beyond Earth. The sheer abundance of water on these planets could provide a fertile environment for the development of life, even if the mechanisms that regulate their climates differ from those on Earth. Future missions and telescopes will be crucial in determining whether water worlds could indeed support life, and they may help us to better understand the range of environments in which life can thrive. The study of exoplanets is also helping scientists to refine the concept of the habitable zone, the region around a star where conditions might be just right for liquid water to exist on a planet's surface. Traditionally, the habitable zone has been defined by the distance at which a planet would receive enough energy from its star to maintain liquid water, without being so close that the water would evaporate, or so far away that it would freeze. However, as astronomers discover more diverse types of planets and planetary systems, they are realizing that habitability might not be so simple. For example, planets with thick atmospheres, like Venus, can experience runaway greenhouse effects that raise their surface temperatures far above what would be expected based on their distance from the star alone. On the other hand, planets with very thin atmospheres or those that orbit dim stars might be able to retain liquid water even if they are farther from their stars than the traditional habitable zone would suggest. The discovery of exoplanets in binary star systems, where a planet orbits two stars instead of one, adds another layer of complexity, as the combined gravitational and thermal effects of the two stars can create unusual conditions for the planet. One of the most intriguing aspects of the search for exoplanets is the possibility that there are planets orbiting stars in the habitable zones that could be remarkably similar to Earth. This notion has inspired countless studies and observations focused on identifying Earth-like planets that might be capable of hosting life. Although no planet has yet been discovered that perfectly matches Earth's characteristics, there have been several tantalizing candidates. One of the most notable is Proxima Centauri b, an Earth-sized planet located in the habitable zone of Proxima Centauri, the closest star to our solar system. Proxima Centauri b is about 4.2 light-years away, making it the closest known exoplanet in a potentially habitable zone. Although it is still unclear whether Proxima Centauri b has an atmosphere or liquid water on its surface, its proximity to Earth makes it a prime target for future exploration. Researchers are hopeful that upcoming telescopes will be able to determine more about the planet's atmosphere and potential for habitability. Another exciting candidate is the TRAPPIST-1 system, which contains 7 Earth-sized planets, 3 of which are located in the star's habitable zone. TRAPPIST-1 is a cool, red dwarf star located about 40 light-years away, and the discovery of its planetary system was a major milestone in the search for Earth-like exoplanets. The TRAPPIST-1 planets are tightly packed around their star, and their close orbits mean that they experience strong gravitational interactions with each other, which could have significant effects on their climates and atmospheres. These planets are among the best-studied exoplanets, and future observations could reveal whether they have the right conditions for life. Red dwarf stars like TRAPPIST-1 are of particular interest in the search for habitable planets because they are the most common type of star in the universe. Although red dwarfs are much smaller and cooler than stars like our Sun, their abundance means that they could host a large number of potentially habitable planets. However, red dwarf stars also tend to be very active, emitting powerful flares and radiation that could strip away the atmospheres of nearby planets, making them less hospitable for life. Understanding how these stellar conditions affect the habitability of exoplanets is a key area of research. The search for life beyond Earth often focuses on planets with conditions similar to those on Earth, but astronomers are increasingly considering the possibility that life could exist in environments that are radically different from anything we see in our solar system. For example, some scientists speculate that life could exist on planets with thick, hydrogen-rich atmospheres, even if those planets are much colder than Earth. The idea is that hydrogen, being the light gas, could provide enough buoyancy to allow microorganisms to float in the upper layers of the atmosphere, where they could capture energy from the star or from chemical reactions. This concept of life as we don't know it challenges traditional assumptions about habitability and expands the range of environments where we might find life. In fact, there may be planets in our galaxy that have conditions so exotic that we can't even imagine what kind of life they could support. The discovery of such planets would revolutionize our understanding of biology and the possibilities for life in the universe. One of the major goals of exoplanet research is to determine how common Earth-like planets are in the galaxy. If planets with conditions similar to Earth are relatively common, it would increase the likelihood that life could exist elsewhere in the universe. However, if Earth-like planets are rare, it might suggest that our planet is truly unique in its ability to support life. This question is often framed in terms of the Drake equation, which attempts to estimate the number of civilizations in the galaxy that we might be able to communicate with. The discovery of exoplanets has provided crucial data to help refine the Drake equation, but many of the variables, such as the fraction of planets that develop life, remain unknown. As we continue to discover more exoplanets, we are beginning to get a better sense of the diversity of planetary systems in the galaxy. While some systems resemble our own, with small, rocky planets orbiting close to their stars and gas giants farther out, others are completely different. Some systems contain planets that are packed closely together, while others have planets with highly eccentric orbits that take them far from their stars for part of their orbits. This diversity suggests that there may be many different pathways to planet formation, and it challenges the idea that our solar system is the default model for how planetary systems form. One of the most exciting aspects of exoplanet research is that we are still in the early stages of exploration. New telescopes and instruments are coming online that will allow us to detect smaller planets, analyze their atmospheres in greater detail, and even search for signs of life. The James Webb Space Telescope, which launched in 2021, is expected to revolutionize our understanding of exoplanets by providing unprecedented views of their atmospheres and climates. Other upcoming missions, such as the European Space Agency's Plato mission, will focus on finding Earth-sized planets in the habitable zones of Sun-like stars. In the future, it's possible that we could send spacecraft to explore exoplanets up close. While the vast distances involved make this a daunting challenge, some researchers are working on technologies that could allow us to send small, lightweight probes to nearby star systems. One such project is Breakthrough Starshot, which aims to send tiny spacecraft to Proxima Centauri using powerful lasers to propel them at a significant fraction of the speed of light. If successful, this mission could provide the first direct images of an exoplanet and its environment. The search for exoplanets and the quest to find life beyond Earth is one of the most exciting scientific endeavors of our time. Every new discovery brings us closer to answering some of the biggest questions in science. How common are habitable planets? Is life a rare phenomenon, or is it widespread throughout the universe? And ultimately, are we alone in the cosmos? While we don't yet have the answers, the rapid pace of discovery in exoplanet science suggests that we may be on the verge of a major breakthrough. As we look to the future, it's clear that the mysteries of exoplanets will continue to captivate scientists and the public alike. These distant worlds challenge our understanding of the universe and our place within it. They force us to confront the possibility that life could exist in forms and places that we have never imagined. And they remind us that, in the vastness of the cosmos, there is still so much left to explore. The discovery of exoplanets has also inspired deeper philosophical and existential questions about humanity's place in the universe. If we eventually discover life elsewhere in the cosmos, whether it is simple microbial life or complex, intelligent civilizations, what will that mean for us? Will it challenge long-held beliefs about human uniqueness, or will it inspire a new era of cooperation and exploration as we seek to understand our cosmic neighbors? These are questions that go beyond science, touching on ethics, culture, and the future of our species. In the search for exoplanets, scientists use a variety of methods to detect planets around other stars. One of the most successful techniques is the transit method, which involves observing a star for periodic dimming that occurs when a planet passes in front of it. This method has been used by space telescopes like Kepler and TESS to discover thousands of exoplanets. When a planet transits its star, it causes a slight dip in the star's brightness, and by measuring the duration and depth of this dimming, astronomers can infer the planet's size and orbit. The transit method has revolutionized our understanding of exoplanets, but it has its limitations. For one, it only works for planets whose orbits are aligned in such a way that they pass directly in front of their star from our point of view. This means that many planets remain undetectable using this method. Additionally, the transit method tells us little about the planet's composition or atmosphere. To learn more about these aspects, astronomers use other techniques, such as spectroscopy, to analyze the light that passes through a planet's atmosphere during a transit. By studying the wavelengths of light that are absorbed or emitted, they can infer the presence of certain gases, which might be indicators of habitability, or even life. Another method used to detect exoplanets is the radial velocity technique, which measures the gravitational wobble that a planet induces on its star. As a planet orbits, its gravity pulls on the star, causing it to move in a small orbit of its own. This motion causes shifts in the star's light, which can be detected as changes in the wavelengths of the star's spectral lines. By measuring these shifts, astronomers can determine the planet's mass and orbit. This method is particularly effective for finding massive planets that are close to their stars, such as gas giants like Jupiter. The radial velocity method was responsible for the discovery of the first exoplanet around a Sun-like star, 51 Pegasi b, in 1995. This discovery marked the beginning of the modern era of exoplanet science, and led to the realization that planetary systems are common throughout the galaxy. Since then, the radial velocity method has been used to detect many more exoplanets, and it remains one of the key tools in the search for planets around other stars. In addition to the transit and radial velocity methods, there are several other techniques that astronomers use to find exoplanets. One of these is direct imaging, which involves taking pictures of planets by blocking out the light from the star. This is an extremely challenging technique because stars are much brighter than the planets that orbit them, and the planets are often lost in the glare of their parent stars. However, advances in technology, such as coronagraphs and adaptive optics, are making it possible to directly image planets in some cases, especially if they are large and far from their stars. Direct imaging has provided some of the first actual pictures of exoplanets, giving us a glimpse of these distant worlds in ways that were previously unimaginable. While this method is still in its infancy, it holds great promise for the future, especially as new telescopes with even more powerful imaging capabilities are developed. Gravitational microlensing is another technique used to detect exoplanets. This method takes advantage of the fact that massive objects, like stars or planets, bend the fabric of space-time, causing light from background objects to be magnified. If a star with a planet passes in front of a more distant star, the gravity of the closer star and its planet can act as a lens, briefly magnifying the light from the background star. By analyzing the light curve of this event, astronomers can detect the presence of the planet and learn about its properties. This method is particularly useful for finding planets that are far from their stars or that are located in regions of the galaxy where other methods are less effective. The variety of methods available for detecting exoplanets has allowed astronomers to uncover an incredible diversity of planetary systems. While the planets in our solar system seem to follow a relatively orderly arrangement, with small, rocky planets near the Sun and gas giants farther out, exoplanet systems often defy these expectations. Some planetary systems have hot Jupiters, massive gas giants that orbit extremely close to their stars, completing an orbit in just a few days. These planets are so close to their stars that their atmospheres are heated to thousands of degrees, causing them to puff up and lose gas into space. The existence of hot Jupiters was one of the first major surprises in exoplanet science, as it challenged traditional models of planetary formation. According to these models, gas giants should form far from their stars, where it is cold enough for ice to condense and provide the raw materials for the formation of a large planet. The discovery of hot Jupiters forced scientists to rethink these models and consider the possibility that some planets migrate inward after they form, moving closer to their stars over time. This process of migration could be caused by interactions with other planets, or with the protoplanetary disk from which the planets formed. In addition to hot Jupiters, astronomers have discovered many other types of exoplanets that are unlike anything in our solar system. Super-Earths are planets that are larger than Earth but smaller than Neptune, and they may have thick atmospheres, deep oceans, or even exotic forms of ice. These planets are particularly intriguing because they could be more common than Earth-sized planets, and might offer a wider range of environments for life to develop. One of the biggest questions in exoplanet science is whether any of these distant worlds could host life. The discovery of planets in the habitable zones of their stars, where conditions might be right for liquid water, has raised hopes that some exoplanets could support life. However, simply being in the habitable zone is not enough to guarantee that a planet is habitable. A planet's atmosphere, composition, and geological activity all play crucial roles in determining whether it can support life. One of the key indicators that scientists look for when searching for life is the presence of certain gases in a planet's atmosphere, such as oxygen, methane, and carbon dioxide. These gases are often produced by biological processes, and their detection on an exoplanet could be a sign of life. However, it is also possible for these gases to be produced by non-biological processes, such as volcanic activity or chemical reactions in the planet's atmosphere. Distinguishing between these possibilities will require detailed observations of exoplanet atmospheres, as well as a better understanding of how life and geology interact on different types of planets. Another potential indicator of life is the presence of liquid water, which is essential for all known forms of life. The search for water on exoplanets has been a major focus of recent research, and there have been several promising discoveries. For example, the detection of water vapor in the atmosphere of the exoplanet K2-18b, located in the habitable zone of its star, has generated significant excitement. Although K2-18b is much larger than Earth and may have a thick atmosphere, the presence of water vapor suggests that it could have conditions favorable for life. Future observations will be needed to determine whether liquid water exists on the planet's surface and whether its atmosphere contains other gases that might indicate biological activity. As the search for life on exoplanets continues, scientists are also exploring the possibility of biosignatures, chemical or physical signs that could indicate the presence of life. Biosignatures could take many forms, from specific combinations of gases in a planet's atmosphere to patterns of light or heat that are difficult to explain through non-biological processes. The development of new technologies, such as advanced spectrometers and space telescopes, will be crucial in detecting these potential signs of life and in determining whether any of the exoplanets we have discovered could be home to living organisms. The discovery of exoplanets has also raised the possibility of finding planets with technosignatures, evidence of advanced civilizations that have developed technology. Technosignatures could include radio signals, artificial light, or even the presence of certain chemicals in a planet's atmosphere that are associated with industrial processes. While the search for technosignatures is still in its early stages, it is an exciting area of research that could yield profound insights into the existence of intelligent life beyond Earth. One of the key challenges in the search for exoplanets is that most of the planets we have discovered are located many light years away, making direct exploration impossible with current technology. However, some of the most promising exoplanets are located relatively close to Earth, and future missions could aim to study these planets in greater detail. One of the most anticipated missions for studying nearby exoplanets is the James Webb Space Telescope, JWST, which was launched in December 2021. JWST has significantly advanced our ability to observe exoplanet atmospheres, thanks to its powerful infrared capabilities. Its ability to detect and analyze the light that passes through a planet's atmosphere during transits allows scientists to look for specific chemical signatures that might indicate the presence of life or other conditions favorable for habitability. JWST's first observations of exoplanets have already begun to shed light on their atmospheres. For instance, it has provided insights into the atmospheric composition of the hot Jupiter WASP 39b, revealing the presence of water vapor, carbon dioxide, and even sulfur dioxide. These findings suggest that the planet's atmosphere is much more complex than previously thought, raising intriguing questions about the processes at play on such distant worlds. As JWST continues its observations, it is expected to identify many more exoplanets with potentially habitable conditions, fueling further investigations into the diversity of planetary environments in our galaxy. Another exciting future mission is the European Space Agency's Aerial, Atmospheric Remote Sensing Infrared Exoplanet Large Survey mission, set to launch in the late 2020s. Aerial will focus on studying the atmospheres of a wide variety of exoplanets, from hot Jupiters to smaller terrestrial planets, by observing their transmission spectra during transits. This mission aims to characterize the chemical and physical properties of exoplanet atmospheres and gain a better understanding of their formation and evolution. By analyzing a large sample of exoplanets, Aerial will help identify trends and correlations between atmospheric compositions and planetary characteristics, contributing to our understanding of the conditions that foster habitability. In addition to space telescopes, ground-based observatories are also playing a crucial role in the exoplanet search. Facilities such as the Extremely Large Telescope, ELT, which is currently under construction in Chile, will have the power to directly image exoplanets and analyze their atmospheres in unprecedented detail. The ELT's advanced instruments will enable scientists to search for biosignatures and technosignatures by observing the light reflected off exoplanets, making it a critical tool in the quest to understand whether life exists beyond Earth. The study of exoplanets is not only reshaping our understanding of planetary systems, but also prompting scientists to reconsider how we classify and categorize these distant worlds. For instance, the discovery of rogue planets, which are planets that do not orbit any star and instead drift through interstellar space, challenges traditional definitions of what constitutes a planet. These rogue planets may form in typical planetary systems, but get ejected due to gravitational interactions or may form independently from stars in the cold depths of space. Additionally, the emergence of new categories of exoplanets, such as mini-Neptunes and super-Earths, suggests that our definitions of planet types must evolve as we discover more about their compositions, atmospheres, and potential for hosting life. Mini-Neptunes are smaller than Neptune but larger than Earth, and they may have thick atmospheres dominated by hydrogen and helium. Super-Earths, on the other hand, can be rocky or gaseous, and their diversity adds to the complexity of understanding planetary formation and evolution. As our understanding of exoplanets deepens, so too does the realization that they may not be as alien as we once thought. Some researchers speculate that certain exoplanets could harbor environments similar to Earth, with the potential for liquid water and organic compounds necessary for life. This has led to discussions about the importance of targeting specific exoplanets for detailed observation, particularly those in the habitable zones of their stars where conditions might resemble those on Earth. The search for exoplanets is not without its challenges. The vast distances involved mean that most exoplanets are still shrouded in mystery, and our current technology limits our ability to explore them directly. Furthermore, the potential for false positives, signals that may resemble biosignatures but arise from non-biological processes, poses a significant hurdle in confirming the presence of life. As a result, scientists are taking a cautious approach, emphasizing the need for complementary evidence before concluding that any detected signals truly indicate life. Despite these challenges, the search for exoplanets and the quest to understand their potential for habitability continues to capture the imagination of scientists and the public alike. The prospect of discovering a planet with life, whether microbial or intelligent, would be one of the most profound scientific achievements in human history. It would challenge our understanding of life, our place in the cosmos, and could lead to groundbreaking advancements in various fields of science. Moreover, the study of exoplanets has practical implications for understanding climate change and the future of Earth. By examining the atmospheres of exoplanets, scientists can learn about the processes that influence planetary climates and the conditions that lead to habitability. This knowledge can inform our understanding of Earth's own climate systems and help us develop strategies for mitigating the impacts of climate change. In summary, the field of exoplanet research is a rapidly evolving frontier of science that offers insights into the nature of planets beyond our solar system. From the detection of thousands of exoplanets to the exploration of their atmospheres and the search for signs of life, this area of study is reshaping our understanding of the universe and our place within it. The discoveries of the coming years, fueled by new technologies and missions, promise to deepen our understanding of the cosmos and bring us closer to answering one of humanity's oldest questions: are we alone in the universe? As we continue to explore the mysteries of exoplanets, we stand on the brink of a new era in our understanding of life beyond Earth, one that could redefine what it means to be human in the grand tapestry of the cosmos. The fascination with exoplanets also extends to cultural and artistic expressions. The discovery of these distant worlds has inspired works of science fiction, art, and music, reflecting humanity's deep-seated desire to explore the unknown and to ponder the possibilities of life beyond our own planet. In literature, authors have envisioned myriad scenarios of alien life, planets with exotic landscapes, and civilizations far more advanced than our own. These imaginative explorations often serve as a reflection of our hopes, fears, and aspirations as we navigate our place in an ever-expanding universe. As we delve into the mysteries of exoplanets, we also confront ethical considerations regarding the exploration of other worlds. If we do discover extraterrestrial life, how should we interact with it? What ethical responsibilities do we have toward these potential neighbors? The notion of planetary protection, ensuring that we do not contaminate other worlds with earthly organisms, is paramount in the planning of future missions. Similarly, the potential for future colonization of exoplanets raises questions about the rights of any indigenous life forms and the ecological implications of human expansion into the cosmos. The excitement surrounding exoplanets reflects a broader curiosity about our universe and the potential for discovery that lies ahead. Each new finding challenges our perceptions, drives scientific innovation, and ultimately inspires us to reach for the stars. As we look to the future, the study of exoplanets stands as a testament to human ingenuity and the unyielding quest for knowledge, reinforcing the idea that while our Earth is our home, the universe is an expansive realm waiting to be explored. The exploration of exoplanets is not just a scientific endeavor, it is a quest for understanding, a journey that intertwines science, philosophy, culture, and ethics. The discoveries we make in this realm will undoubtedly shape our understanding of life, the universe, and our place within it. As we continue to uncover the secrets of these distant worlds, we embark on a journey that transcends the boundaries of our planet, inviting us to contemplate the vastness of the cosmos and the myriad possibilities it holds. The mysteries of exoplanets are far from solved, and as technology advances and our exploration efforts expand, we can only imagine what new revelations lie ahead. The universe is a vast and wondrous place, and the search for exoplanets is just the beginning of a journey that promises to change everything we know about life in the cosmos. As we venture further into the study of exoplanets, one of the most profound areas of exploration is the search for Earth-like worlds within their respective habitable zones. The habitable zone, often referred to as the Goldilocks zone, is the region around a star where conditions may be just right for liquid water to exist on a planet's surface. The discovery of Earth-like exoplanets in this zone is pivotal because water is considered essential for life as we know it. Identifying such planets not only broadens our understanding of potential life-sustaining environments, but also provides new targets for future explorations. One of the most notable examples of an Earth-like exoplanet is Proxima Centauri b, which orbits the closest star to our solar system, Proxima Centauri. Proxima Centauri b is located within the star's habitable zone, making it a prime candidate for further investigation. However, the planet's actual conditions are still uncertain due to its proximity to a red dwarf star, which can emit powerful flares that could strip away a planet's atmosphere. Future observations will be crucial to determining the viability of Proxima Centauri b as a potential host for life. Another intriguing target in the quest for Earth-like exoplanets is the TRAPPIST-1 system, which contains 7 Earth-sized planets, 3 of which are located in the habitable zone of their star. The TRAPPIST-1 system offers a unique opportunity to study a variety of planetary environments and assess their potential habitability. Understanding the diversity of these planets, including their atmospheric compositions and geological characteristics, could provide insights into how life might arise in different settings. The concept of a superhabitable planet has also emerged as a fascinating area of speculation. This theory suggests that some exoplanets might possess conditions that are not just suitable for life but could be even more favorable than those on Earth. Such planets might have more stable climates, a greater abundance of essential minerals, or unique geological features that could foster diverse ecosystems. While this idea is still largely theoretical, it opens the door to considering a broader range of possibilities for habitability beyond our own planet. The implications of discovering potentially habitable exoplanets extend beyond scientific inquiry. They provoke philosophical questions about the nature of life and our role in the universe. The existence of life elsewhere could fundamentally challenge our understanding of biology, evolution, and the uniqueness of the human experience. As we ponder these possibilities, we must also consider how we, as a species, would respond to the knowledge that we are not alone. The ethical considerations surrounding our exploration of other worlds become even more pressing as we venture into the realms of potential extraterrestrial life. Another critical aspect of exoplanet research is the development of new techniques for detecting and characterizing these distant worlds. One such technique is called direct imaging, which allows astronomers to capture the light reflected from an exoplanet rather than relying solely on indirect methods such as the transit method or radial velocity measurements. Direct imaging is particularly valuable for studying the atmospheres of exoplanets and searching for biosignatures. In direct imaging, telescopes utilize specialized instruments to block out the light from the host star, allowing the much fainter light from the exoplanet to be observed. This technique is challenging due to the overwhelming brightness of stars and the need for precise alignment and stabilization of the telescope. However, advancements in adaptive optics and coronagraphy are making direct imaging increasingly feasible. This method has the potential to provide direct evidence of atmospheric components, such as methane or oxygen, that could indicate biological processes. As technology advances, the prospects for characterizing exoplanets become more promising. Instruments like the upcoming Habitable Worlds Observatory, planned for the 2030s, aim to expand our ability to directly image and analyze exoplanet atmospheres. This observatory will focus on identifying biosignatures and assessing the habitability of a wide range of exoplanets. The possibility of detecting signs of life beyond Earth would not only be a groundbreaking scientific achievement, but also profoundly impact our understanding of our place in the universe. Additionally, machine learning and artificial intelligence are playing an increasingly important role in exoplanet research. These technologies can analyze vast amounts of data collected from telescopes and satellite missions, enabling astronomers to identify patterns and anomalies that may indicate the presence of exoplanets or potential biosignatures. Machine learning algorithms can sift through the noise and light curves, enhancing the efficiency of exoplanet detection and characterization. As we look to the future, the international collaboration of space agencies and research institutions is critical for advancing our understanding of exoplanets. The European Space Agency, NASA, and various universities worldwide are working together to share data and resources in the pursuit of exoplanet research. Collaborative efforts have led to the establishment of various space missions and observatories, increasing our collective ability to explore the cosmos. The prospect of sending missions to study exoplanets directly is also an area of active exploration. Concepts for interstellar probes capable of traveling to nearby star systems have been proposed, such as the Breakthrough Starshot initiative. This ambitious project aims to develop a fleet of tiny spacecraft that could be propelled by powerful lasers to reach Proxima Centauri in just a few decades. Although this endeavor is still in its early stages, it exemplifies the human drive to explore the universe and understand our place within it. As our understanding of exoplanets deepens, we are reminded of the vastness of the cosmos and the incredible diversity of planetary systems that exist beyond our solar system. The continued exploration of these worlds not only enhances our scientific knowledge, but also inspires future generations to reach for the stars. The mysteries of exoplanets are a testament to humanity's curiosity and the relentless pursuit of understanding, pushing the boundaries of what we know about life, our planet, and the universe. The future of exoplanet research holds immense promise, with the potential for groundbreaking discoveries that could reshape our understanding of the universe. As we develop more advanced technologies and methodologies for exploring distant worlds, we stand on the brink of a new era in astronomy and planetary science. Each new discovery brings us one step closer to answering some of humanity's most profound questions. Are we alone in the universe? What forms of life might exist on other worlds? How do planetary systems evolve, and what conditions foster the emergence of life? In this quest for knowledge, the study of exoplanets transcends mere scientific inquiry. It is a journey of discovery that invites us to ponder our place in the cosmos and reflect on the nature of existence itself. As we continue to explore the mysteries of exoplanets, we are reminded that our search for understanding is as much about the human experience as it is about the universe we inhabit. The quest for exoplanets is not just about finding new worlds. It is about expanding the horizons of human knowledge and embracing the possibilities that lie beyond our planet. As we navigate this complex and ever-evolving field of study, it is essential to engage the public in the conversation surrounding exoplanets and their significance. Public outreach and education efforts can foster a deeper appreciation for the wonders of the universe and inspire curiosity about science and exploration. By sharing the stories of exoplanet discoveries and the scientists behind them, we can encourage future generations to pursue careers in science, technology, engineering, and mathematics (STEM) fields. Furthermore, the cultural implications of exoplanet research can be explored through various forms of media, including literature, film, and art. Science fiction often serves as a vehicle for expressing our hopes, fears, and aspirations regarding life beyond Earth. These narratives provide a platform for contemplating the ethical and philosophical dilemmas that may arise from encountering extraterrestrial life or colonizing other worlds. Engaging with these themes can enrich our understanding of what it means to be human in a vast and diverse universe. The search for exoplanets is a reflection of humanity's enduring quest for knowledge and understanding. It embodies the spirit of exploration that has driven our species for millennia, from the early voyages across oceans to the advent of space travel. Each new discovery in the realm of exoplanets not only advances our scientific knowledge, but also deepens our appreciation for the beauty and complexity of the cosmos. In conclusion, the exploration of exoplanets represents one of the most exciting frontiers of modern science. As we unravel the mysteries of these distant worlds, we embark on a journey that challenges our understanding of life, the universe, and our place within it. The ongoing research and discoveries in this field promise to reshape our perceptions, inspire future generations, and ultimately bring us closer to answering one of humanity's most profound questions: are we alone in the universe? As we continue to push the boundaries of exploration and understanding, the search for exoplanets serves as a reminder of the limitless possibilities that lie beyond our planet, waiting to be discovered. The search for exoplanets has also been significantly enhanced by various space missions that have dedicated themselves to discovering new worlds. One of the most groundbreaking missions was NASA's Kepler Space Telescope, launched in 2009. Kepler revolutionized our understanding of exoplanets by employing the transit method, which detects tiny dips in a star's brightness caused by a planet passing in front of it. This method allowed Kepler to identify thousands of candidate exoplanets, many of which were found to be similar in size to Earth. The Kepler mission has provided a treasure trove of data that scientists continue to analyze, revealing the incredible diversity of planetary systems and their configurations. Following the success of Kepler, the Transiting Exoplanets Survey satellite, TESS, launched in 2018, has taken up the mantle of exoplanet discovery. TESS is designed to monitor bright stars near Earth, allowing it to identify nearby exoplanets that can be studied in greater detail. By focusing on stars that are closer to us, TESS increases the chances of finding exoplanets that can be observed with follow-up missions, making them ideal candidates for atmospheric characterization. This mission complements Kepler's work by providing a new generation of exoplanets for study, particularly those that might lie within our own cosmic neighborhood. The James Webb Space Telescope, JWST, launched in December 2021, marks another significant advancement in our quest to understand exoplanets. With its powerful infrared capabilities, JWST can analyze the atmospheres of exoplanets in unprecedented detail. One of its primary scientific goals is to investigate the chemical composition of exoplanet atmospheres, searching for potential biosignatures like water vapor, carbon dioxide, and methane. The ability to study exoplanet atmospheres will be crucial in assessing their habitability and the potential for life. JWST's observations will also provide insight into the formation and evolution of planetary systems. By studying young stars and their surrounding protoplanetary disks, scientists can gather data on how planets form and migrate within their systems. Understanding these processes is essential for developing models that explain the diversity of planetary systems we observe today, including the stark differences between gas giants, rocky planets, and potentially habitable worlds. The discovery of exoplanets has prompted a re-evaluation of how we understand planetary formation. The traditional model of planetary system formation suggests that planets form from a disk of gas and dust surrounding a young star. However, observations of exoplanets have revealed a wide range of planetary types and arrangements, including hot Jupiters, gas giants that orbit very close to their stars, and tightly packed systems of Earth-sized planets. These discoveries challenge existing models and require scientists to rethink the processes that lead to the formation of different types of planets. Moreover, the study of exoplanets has unveiled the phenomenon of planetary migration. This process refers to the movement of planets from their original formation locations to new orbits within their systems. For instance, hot Jupiters are believed to have formed far from their stars before migrating inward. Understanding planetary migration is crucial for explaining the diversity of planetary systems and assessing the potential habitability of Earth-like planets in various environments. As we delve deeper into exoplanet research, the search for signs of life becomes a central focus. The field of astrobiology is intimately connected to exoplanet studies, as it seeks to understand the potential for life beyond Earth. Scientists are exploring the conditions that might support life, from extreme environments on Earth, such as deep-sea hydrothermal vents and acidic lakes, to the theoretical possibilities for life on exoplanets with diverse climates and atmospheres. The concept of biosignatures, is fundamental to the search for extraterrestrial life. Biosignatures are indicators of biological activity, which can include gases such as oxygen, methane, or nitrous oxide. The presence of these gases in an exoplanet's atmosphere could suggest the existence of life forms capable of producing them. However, interpreting these signatures requires careful analysis, as certain abiotic processes can also produce similar atmospheric constituents. For this reason, researchers are working to refine their understanding of how to distinguish between biological and non-biological sources of these gases. The investigation of exoplanets has also revealed the possibility of life in unexpected places. For example, moons in our own solar system, such as Europa and Enceladus, are considered potential candidates for hosting life due to the subsurface oceans beneath their icy crusts. The study of these moons, combined with exoplanet research, expands the search for life beyond traditional planets. Understanding the environments that could support life will inform the design of future missions aimed at exploring these intriguing locations. Moreover, the cultural and philosophical implications of discovering life beyond Earth cannot be overstated. The possibility of encountering extraterrestrial life forces us to confront profound questions about humanity's place in the universe and our relationship with other potential life forms. It invites speculation on how such a discovery would reshape our understanding of ourselves, our biology, and our place in the cosmic hierarchy. The implications of contacting intelligent extraterrestrial civilizations are equally significant, challenging our concepts of society, ethics, and communication. As we continue to explore the mysteries of exoplanets, the advent of new technologies will further enhance our capabilities. Projects like the European Space Agency's Ariel mission, set to launch in the late 2020s, aim to study the atmospheres of exoplanets in detail. Ariel will focus on measuring the composition, temperature, and clouds of a diverse sample of exoplanets, providing crucial insights into their formation and potential habitability. Moreover, the potential for discovering biosignatures will increase with the upcoming generation of ground-based telescopes equipped with advanced adaptive optics. These observatories will complement space missions and allow for detailed studies of nearby exoplanets. The combination of ground and space-based efforts will usher in a new era of exoplanet research, where the capabilities to observe and analyze distant worlds will be unparalleled. As we look to the future of exoplanet research, the collaborative efforts between nations and scientific institutions will play a crucial role in advancing our understanding of the cosmos. International partnerships are essential for sharing resources, data, and expertise in the pursuit of exoplanet discoveries. By pooling our collective knowledge, we can tackle the complex challenges of exoplanet research and expand the horizons of our understanding. In summary, the exploration of exoplanets is an ongoing journey filled with discoveries that continuously challenge our understanding of the universe. The identification of potentially habitable worlds, the search for biosignatures, and the examination of planetary formation processes offer a glimpse into the vast diversity of planetary systems that exist beyond our own. As we strive to unravel the mysteries of these distant worlds, we remain committed to answering fundamental questions about life, habitability, and the nature of our existence in the cosmos. The pursuit of knowledge in this field is not just an academic endeavor, it is a testament to humanity's unyielding curiosity and our desire to explore the unknown. The study of exoplanets reminds us of the vastness of the universe and the myriad possibilities that lie beyond our planet. Each new discovery adds to the tapestry of our understanding, revealing the complexities of planetary systems and the potential for life in diverse environments. As we continue to advance our technologies and methodologies, we stand poised on the brink of groundbreaking discoveries that will undoubtedly reshape our understanding of the universe and our place within it. With each step we take in the exploration of exoplanets, we are reminded of the richness of the cosmos and the uncharted territories that await our discovery. As we look ahead to the future of exoplanet research, we remain hopeful that our efforts will yield new insights, inspire future generations, and ultimately lead us to answers about life beyond Earth. The mysteries of exoplanets serve as a powerful reminder of the endless possibilities that exist in the universe, urging us to continue our quest for knowledge and understanding. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.